Assalamu alaikum. My name is Mubin Malik and today we are going to implement half adder, half subtractor, full adder and full subtractor, and we will verify their truth tables using Proteus. So if you look at the truth table of half adder here, these are the two inputs, 1-bit inputs, and this represents the sum, this column represents the sum, and this column represents the carry. Now if 0 is added to 0, we get a 0 at the sum and the carry is also 0. If 0 is added to 1, then we get 1 at the sum and 0 carry. If 1 is added to 0, then we get again the sum as 1 and the carry as 0. Now if 1 is added to 1 in binary, it becomes 0 and a carry is generated, which you can see is written in this column. Now we will make the circuits using simple equations from this truth table, and those simple equations will be then converted into NAND gates, and then the same circuit, the same truth table will be implemented on by using the NAND gates. So if I show you here, this is the implementation of the half adder. This is the equation we will get, which basically is the A XOR B. The carry is equal to AB, and the NAND implementation is just converting these equations back into their NAND form. When double complement of this equation is taken, this equation becomes which is in the NAND form, and same goes with this carry equation. Now I will explain all the truth tables to you first, and then I will verify the truth tables using the Proteus. The second truth table is of the half subtractor. 0 minus 0 is 0, D is the difference, and B is borrow if needed. Now to subtract B from A, you can see 0 is a smaller number and 1 is a greater number, so there needs to be a borrow. So borrow comes here, this becomes 1 0 minus 1, 2 minus 1 is equal to 1, and 1 borrow here. Now 1 minus 0 is simply 1, and 1 minus 1 is simply 0, and there is no borrow needed for these two. For the NAND implementation, and if I show you the equation of half subtractor, this is the equation of half subtractor, and this is the equation for its borrow. This is the complete derivation of the original equation into NAND form, and this is the same implementation of into NAND form of the borrow output. Now the next truth table is of the full adder and the full subtractor. Here we have A and B as two inputs. C in is the carry in from an other adder probably, or any other circuit, as is the sum, and C out is the carry out. Now if 0 plus 0 plus 0 is equal to 0, and there is no carry, so 0 here. 0 plus 0 plus 1 is equal to 1 with no carry. Same goes here, sum is 1 with no carry. Now 1 plus 1 gives a 0 at the sum but a carry as 1. Now again 1 plus 0 is equal to 1. 1 plus 1, sum is 0, carry becomes 1, and same goes here. In this case 1 plus 1 is equal to 0. 0 plus 1 is equal to 1, which is the sum, and we have to take 1 carry here when we added 1 into 1. So this carry right here is that. The truth table of full subtractor, but first let me show you the implementation into NAND of the full adder. This is the full adder, and this becomes the equation A XOR B XOR C, and this is the equation of the carry output. After the NAND implementation, this A XOR B is replaced by X, so the S becomes X XOR C, and then this same procedure is followed where we take the double complement of the original equation. Same goes here with the carry output, and we have the NAND implementation for this circuit. Now if we see the truth table of full subtracted, 0 minus 0 minus 0 is equal to 0, and we don't have to take a borrow. 0 minus 0 is equal to 0, and then again to minus 1 from 0 we have to take a borrow, which is here, and then the difference becomes 1. The same goes here. To minus 1 from 0 we have to take a borrow, and the difference becomes 1, and 1 minus 0 is equal to 1 still. So this right here is the difference, and this is the borrow that we had to take. 0 minus 1 is a borrow, so we have taken a borrow here, and this 0 minus 1 becomes 1, and 1 minus 1 then becomes again 0. 1 minus 0 is equal to 1. 1 minus 0 minus 1 is equal to 0. 1 minus 1 is equal to 0, and 1 minus 1 becomes 0, and then again 0 minus 1 we have to take a borrow right here, and then 0 minus 1 is equal to 1. This is the implementation of full subtractor. As you can see, the difference is the same as the sum in the full adder. The full adder right here, the equation for the sum and the difference is same for both circuits. The difference comes when borrow is taken. So for the NAND implementation, these steps are followed, where we have to reduce the circuit into the form where there is not a single OR gate involved, and the double complement helps us to convert the circuit or the equation into a full NAND form. Now I will show you the implementation on Proteus. So the first circuit I'm going to show you is of a full adder. Now this is the first input A, and this is the first input B. This LED represents the sum. Same goes for here, and these two LEDs represent the carry out. So if I give a single digit 1, you can see the sum becomes 1, and there is no carry because 1 plus 0 is equal to 1. Now same goes for here, but if I press both of the switches, which means 1 plus 1, now the sum becomes 0 as evident from this truth table, but the carry becomes 0. These two LEDs mimic the same behavior, which actually means that both these circuits are same, as they are connected to the same inputs and give out the same outputs. Now the next circuit that we have to verify is of the half subtractor. Same goes for here, as this becomes the first input, this is the second input, and these LEDs, this LED represents the difference, and this LED represents the borrow, if any. So if I run the circuit, and now 1 minus 0 is actually 1. 0 minus 1 is 1, but with a borrow 1. 1 minus 1 is equal to 0 with no borrow. So this also verifies this truth table. The next circuit is of a full adder. Now this is the full adder circuit. This is the carry in input, this is the first input A, and this is the second input B. This LED represents the sum, and this represents the carry. Same goes for here, as you can see they are labeled. Now if I run the circuit, now let's verify. 0 plus 0 plus 1 is equal to 1, and without any carry. 0 plus 1 plus 0 is equal to 1 without any carry. Now 0 plus 1 is equal to 0 with a carry 1, as you can see from this truth table. 0 plus 1 is equal to sum is 0 with a carry 1. Now let's see these four inputs, where A is 1, and we have to change these inputs. Now here, if I turn the A on and then turn the carry in, if this becomes 1, then you can see from the truth table 1 plus 0 plus 1 has a carry 1, but sum is equal to 0, which is also shown here. Now 1 plus 1 plus 0 is having the same results. 1 plus 1 plus 1 is equal to actually a 1, where the sum is 1 and the carry also is a 1. The next circuit we have to verify is, which actually is the last circuit, is the full subtractor. For the full subtractor, these three are the three inputs. This is the borrow, this is the most significant A, and B is the lesser significant input. We will be doing A minus B throughout this demonstration. So if borrow is equal to 1, we have to run the circuit first. If borrow becomes 1, you can see from this truth table that difference becomes 1 with a borrow 1, because we have to take a borrow, as I have explained earlier. Now if B becomes 1, same results. Now if both of them become 1, then we have a difference as 0, as you can see from this truth table, but the borrow still remains 1. For the next part, we will turn A as 1, and you can see 1 minus 0 is equal to 1 with no borrow. 1 minus 1 is equal to 0 without any borrow. Same goes for here. And 1 minus 1 minus 1 actually gives out a difference of 1, and there has to be a borrow taken, because 1 minus 1 becomes 0, and we have to take a borrow to subtract it, to subtract this one from this 0. So this was my implementation of NAND gates and normal gates for full adder, full subtractor, full half adder and half subtractor. Thank you very much. Allah Hafiz.